All right, so wait for the timer to count down here. I put this at a 3:45 start. That's California time. And boom. Okay, it just disappeared, I guess. Let me toggle off the timer. Welcome and hello. This is a HEC RAS lecture. I'm going to be covering the topic of 1D study flow, as you see on the screen here. And what I'm going to be doing is just going through an example problem, but in the lecture format, which allows users to ask questions via chat and come and go as they please. And I'll most likely have this video available on the channel after it is done recording. All right. So let me go ahead and close that. Open up my HEC RAS. I thought I already had it opened up here. 1 second. I'm using HEC RAS version 6.6. And what we have here is the main user interface. You can use a more recent version of HEC RAS, or really any version that starts with a 6 point would probably be just fine. All right. If you're brand new to HEC RAS, never heard of this program before, that's not a problem. You can just Google HEC RAS, and what you're going to see is the first hit, HEC RAS Hydraulic Engineering Center. This is the river analysis system software that HEC has put out. And if you want to download the program, go ahead and click on downloads in the left menu here. And then you can click on the 6.7 beta 2, 6.7 beta, or what I'm using here is HEC-RAS version 6.6. Okay. And anyway, this is not a lecture on how to download and install the software, but I just wanted to point that out to you. It's going to be your first hit on Google if you type in HEC-RAS. All right. So now what we have here is our user interface at the top. This is the main file uh, user interface, which identifies the different file plans, the geometry, flow file, and so on, as well as the actual file path. What you'll see in this left column is the title of that file. And then if you want to edit the geometry, for instance, you can go up to Edit Geometric Data Editor. This is a separate window that's going to pop up on the screen here. It's mobile. I just happen to have it right down here, but you can resize it and move it around just by dragging on the frame and the edge of the frame as well. Okay, now we're not going to be covering 2D or RAS Mapper in this particular lecture, but I did want to point out if you go up to GIS Tools, RAS Mapper, that opens up a similar separate dialog box that you can use to generate terrains and perform a number of other features associated with the geometry. Okay, but we're going to be sticking with the geometric data editor. This is all we need for a 1D model. And not only are we doing 1D in this lesson, we're doing 1D study flow. All right. So anyway, if you have any questions during this stream, go ahead and type them in the chat. I have that open up in my other monitor here, so I'm keeping an eye on that. And if you don't, that's all good. Let's go ahead and get started. So to do that, we'll go up to File and then New Project. And then next, what we want to do here is identify where on our computer or our network that we want to save our project. So go ahead and use this navigation window here. I'm going to put this in my HEC-RAS lectures, and then one, and then project. Okay. Then over here in the title field, give it a title, something like lecture one, and then click OK. All right. This is just a quick dialog box to confirm the units are US customary units for me. So I'll click OK. Oops. And sometimes it seems to always close my geometric data editor. No problem. I just click on the button right here to open that back up. All right. So we are rocking and rolling. We've created a project. Next, what I want to do is create a geometry file. So down here in the geometric data editor, that's where I'm going to be doing that. It's not going to be geo-referenced, so we're going to be entering some of the length data and the spatial data in tables instead of referring to some downloaded DEM or GIS data. All right, so to do that, we're going to come down here to the geometric data editor, click on the river reach button here at the top. Along the top, you're going to see buttons for creating different elements, and then along this left panel is for creating and also editing existing elements. That's sort of the theme there. I'm not going to be talking about every single button or menu item in this lecture or in any particular lecture. What I'm going to be doing on these lectures is focusing on one specific um, topic and then only describing the tools that you need to know about to accomplish the task at hand. So sometimes I'll go on a little side quest and make some auxiliary discussions or descriptions of things. But for the most part, I'm only going to tell you what you need to know. And if you have questions, go ahead and add them to the chat. All right. So anyway, with this uh, river reach button selected, then see button. Okay. Then just go ahead and do a single left click at the top of the reach. And then I'm going to add some additional left clicks right here just to give the river some curvature. And then at the very bottom, I'm going to do a double click and then boom, there's my river reach. It's now asking for a river name and river A, reach one. That's fine. Then I'll go ahead and click OK. There is the river reach and it's looking good. I can zoom out or zoom in. Oops. Okay, I guess it's not letting me zoom out with the or with the mouse roller tool. But if you do want to zoom out, you can click on this view menu and then set schematic plot extents. And then now what I'm seeing here is just a 0 by 1 window. And what that means is that's sort of the default. So basically it thinks our river is only like 1 foot long. Not a problem. I'm just going to change the zeros to a -1 and then the ones to a 2. So we're basically tripling the X and Y extents of our view here. And this is the same reach. We're just zoomed out a little bit further. But don't worry about that. Our river will be a lot longer than just 1 foot long because we're going to edit that data right now. All right, so here is our river from a plan view. We're looking down on it. Next step is to click on this cross-section button. And see, can you see that all right on the screen? Yeah, it's almost too big. I'm just playing with the controls here. How about right there? Okay, that's fine. Let's give that a shot. Here we have a dialog to define our cross-section geometry for this particular river reach, or any river reach. We select the river here, the reach here, and then to create our first cross-section, we're going to go up to Options and then Add New Cross-Section. This dialog box is asking us what is the river station for this newly created cross-section. And I just typically get in the habit of typing 0 for my first cross-section, which is defining the cross-section down here at the downstream end of the reach. So go ahead and click OK. Next step is to specify the station and elevation data. We can do that right here. So you can just type it in, or if you're like me and have a lot of this data saved in Excel, which I do, I'm just copying it onto my clipboard and on my other monitor, highlighting these cells and then clicking paste. So these are the numbers I'm using. You're welcome to use the same numbers if you want to follow along. Here, I'll make that a little bit bigger. There we go. And I'll just give you a moment to type those numbers in. All right. Once those numbers are typed in, you can click on the Apply Data button. And then over here in the right panel, we see a sketch. Can you see that all right? Nope. Just drag that right there. There we go. So now we see a sketch of that cross section. Keep in mind this particular cross section is exaggerated in the vertical dimension, or I should just say the elevation scale and the stationing scale is different. So it's not quite it doesn't look this way in real life. It'd be much wider. All right. The next step is to specify the downstream distance to the next cross section. This is the downstream most cross section, so I'm just going to type 0 here for this first cross section. And then Manning's end value, I'm just going to type in 0 0.05, 0 0.03, and 0 0.05 for the left overbank main channel and right overbank respectively. That is how, those are just some typical numbers, not really the focus of this lecture, so I'm just going to go with those numbers. All right, the left and right overbank station values right here, this refers to this station value of 60 and this station value of 150. So in the table, that's referring to this record and this record. So I'm going to go ahead and type in 60 cab 150 tab, and then apply data. Okay. And now we have the little red dot here in the bank station legend. It shows you those are the left and right overbank stations. By the way, if you don't see this side panel that's showing up here, you can toggle that on and off by clicking on this button right here. So I think by default it's typically on, but for whatever reason, if it's toggled off, that's how you can see your cross section. All right. There are a number of other tools in this dialog box I'm not going to talk about. We can cover that in a later lesson unless there's a question in the chat. I don't see anything yet. That's cool. But next I want to do is create a cross section at the upstream end of the reach. So what you're seeing here is the downstream end of the reach. Let's go ahead and create a cross section at the upstream end of the reach, and then we'll be ready to interpolate and add a few intermediate cross sections. All right. So to do that, we can just go up to options, add new cross section, and then it's going to ask us for the river station. But what I typically do when I already have a cross section created and I don't want to repeat any of the extra data that's not going to change between cross sections, I think it's a little bit quicker to just go up to options and then copy current cross section. All right, so what it's now asking is what river, what reach, and what is the river station? So we only have one river, we only have one reach. That's pretty trivial. The river station, this is the distance upstream from the end of the reach. And I'm going to go ahead and type in 1000. Okay, so click OK. And then now what we need to do is just, we have our second river station cross section now at river station 100. They are currently identical data except for the river station number. And the only thing I really want to change here is the distance downstream. So we'll just type in 1000 feet, and then I'll copy that over for the main channel on the right overbank as well as increase the elevation right here. So to increase this elevation, we could just type it in, but if you happen to have lots of values, then the quicker way to do that is to go up to options, adjust elevation, and then just type in how about 2 feet. So that will add 2 to all these numbers here in the elevation column when I click OK. All right, boom, there it is. All right, looking good. So over here in the plot, we can actually look at this plot as well. Basically the same data, and we can toggle between our two different cross sections. Now it doesn't look like there's any difference. See, yeah, as I toggle between the two cross sections. And the reason because it's the exact same shape and this elevation scale is changing by about 2 feet, correct? Yeah, it's changing by 2 feet. Now, if you're like me and you don't like that, then you can change the view so that the vertical axis is fixed. And to do that, I think you just go right click and then hold on a second. I think options. Okay, hold on a sec. I must be thinking, oops, cross sections, this view right here. So right click, here it is, set persistent scale. Let me see, did I have set persistent scale here? I did not. Okay. Yeah, so I guess it's only from, I'm sorry, cross section, this view right here. If I go right click, set persistent scale, and then now what I want to do here, let's put a minimum vertical elevation of 30, and how about a maximum of 50? Okay, so that's for Y minimum. It says 32. I'm going to type in 30. And then for Y maximum, I'll go ahead and type in 50. We'll keep everything else the same. So the Y axis increment is 2. Just make sure you can see that. And then I'll go ahead and click OK. All right. So the scale is now reset to the numbers we set it to, and it's also fixed. So now if I change this to River Station 1000, it's higher up. Okay, so this is the downstream, this is the upstream. It's not much of an elevation change. It's only 2 feet over the total length of 1,000 feet for a 0.2% slope change. All right. All right, I'm going to go ahead and close the cross-section editor. And now what we see here in the plan view in the main geometric data editor window here is our two different cross sections. There's one at, let's see, sorry. Yeah, there's one at the bottom here, River Station 0, River Station 1000. That may be good enough. Typically, you do want to have cross sections every more often than 1000 feet. You know, it kind of depends on the river that you're dealing with. Maybe every 100 feet or 200 feet. you could probably get away with a cross section every 400 or 500 feet if there really isn't much change. But the more change in the geometry of the channel, the more cross sections you're going to want to include in your model to capture the change of the geometry because, of course, that affects the flow. Alrighty. So what I want to do is add in some intermediate cross sections, and we're not going to go through the same process 10 more times, but I do want to add a 100-foot spacing between cross sections, and there's a tool to do that here in the geometric data editor. Just go ahead and click on Tools, and then click on Cross Section Interpolation. Within a reach or between two cross sections, it's actually the same for my particular situation because I only have two cross sections, but I'll click on Within a Reach. And then what I have on this screen, this dialog box that popped up, is the river, the reach, and then the upstream and downstream cross sections between which I want to add these intermediate cross sections. So, I just use all river stations. It's basically the same thing as the upstream and downstream most cross sections. The next field down here is maximum distance between cross sections. So I'm going to go ahead and type in 100 feet. And that's really all I need to do besides clicking this Interpolate Cross Sections button. Boom, and then click Close. All right, here are our intermediate cross sections. So they're spaced 100 feet apart. There is a little asterisk right here. I don't know if you can see that on the screen, but that just identifies it as an interpolated cross section. That doesn't mean we can't go ahead and make changes though. So if I click on cross section data editor now we see all of our intermediate cross sections added to this drop down. And then as we toggle through them, so I'm on the upstream-most cross section. This is 900, 800, 700, 600, and all the way down. You can see that not only is the elevation values changing here, but the display is also changing. Oh, it looks like I've hit the bottom. So let's go back to the top, and then water is going to be flowing in the downstream direction. All right. All right. So that is, I think, all we need to do for the geometry for this example problem for 1D steady flow. Pretty straightforward, pretty simple. Lots of other tools available to us to add detail to our cross section and our geometry if we wanted to, but we're not going to be doing that here in this lecture one. One more thing we do want to do in lecture one is save the geometry file. So if I go up to um, the file GUI up here, you can see that we have the project is titled lecture one. This is the file path, at least as I've saved it on my computer. And then we also have a few other files here, the plan, the geometry, the steady flow. We don't even have our geometry file saved yet. And let me open up my project directory. Oops. Is that what I want to do? 1 second. Yeah, okay. So here's my project directory. The only thing in there is this lecture1.prj. But once I add in the, stick that right there. Once I go ahead and save the geometry file, I should get a geometry file saved in my project directory. It's, I believe, going to be have a file extension .g01, like lecture1.g01, and I'm also going to see it up here in my my list of files. So let's do that. File, save geometry data, and then the title is going to be called, I'm just going to call it base, just something generic. And it's saved, yes, into my project directory. Click OK. So base is the title. Here is the file path and lecture1.g01. Sure enough, here is that file. All right, pretty straightforward, right? Yeah. Okay, I got a chat. I just saw it. Sorry if it's been there for a while. How can we obtain hydrologic data using meteorologic data? Okay, so that's I believe that's more of a HEC HMS question if you're talking about taking rainfall data and converting it into a hydrograph. That's going to be, added to your river system. Kadir, if that's your question, that's definitely a topic for a lecture, later lecture, typically in HEC HMS. HEC RAS, which is the software I'm describing now, is basically modeling water that's already in a river and also water over overbank and floodplains. if that makes sense. So great question. And if you have a specific question about the lecture, then I can kind of detour and tell you more about the lecture and answer it in a little bit more detail. But I guess my answer to how we convert rainfall data to runoff, that's really the whole purpose of HEC HMS. So if you're familiar with this YouTube channel or not, doesn't matter. Go ahead and click on the playlists or any of the videos that say Heck HMS. And if you had any follow-up questions, by all means, go ahead and add them to the chat and I'll take a look at them. Okay, good question. So anyway, we've got the project, we've got the geometry, and next up, let me go ahead and close that, is the flow data. So the plan for 1D steady flow needs to have a geometry and some flow data. To define the flow data, go ahead and go up to the edit menu up here and then click on steady flow data. Now there's also options for quasi unsteady flow and unsteady flow. We're going to go ahead and talk about that in later lessons. These three flow buttons, so let me just open up steady flow data. This is the dialog box that I'll be using right down here. But you can also access this dialog box by these three buttons right here. So there's steady flow, quasi-steady flow, and unsteady flow. Sorry, I've got just learning how to do this right here. Yeah, you bet. So here is the top. And so let's go ahead and, yeah, if you hover over the button as well, it is going to give you a little title message. So you're not completely lost as to what it means, or maybe you forgot. But yeah, this is the one we want, view/edit steady flow data. Okay, let me go ahead and just drag that right down here. Hopefully that is visible to you guys viewing. All right, steady flow data. What we're going to be doing is specifying how much flow is in the river at every single reach. The default gives us one single profile and one single cross section. Now we can increase the numbers of profiles and cross sections, and I'll show you how to do both of that. And then we can run the simulation with multiple profiles and multiple cross section data. So let's just say, for instance, we have 100 CFS. Sorry, it's 1,000. Boom. That's really all we need to do. In fact, I can go File, save the flow data. Again, I'm going to call this, oops, I'm going to call this base, and then click OK. Now up here in the top, we have base for our steady flow data. We have lecture1.f01, and I should see that file right here. And boom, right here, this last file here is the flow file, 1 kilobyte. So there's really not a whole lot of information there. I believe it is a text-based file. So let's just see what it looks like. Probably shouldn't be digging into these files, but this is it right here. I'm using HEC RAS 6.6. And then, yeah, so just a constant 100 CFS. Okay, yeah, probably not advisable to be messing around with these files, but the computer science major in me wants to dig in and change stuff. All right, say for instance, we have 100 CFS flowing in from the top of the reach, and we have some additional inflow coming in at river station 800. Let's, okay. So what that would look like here is if I wanted to add that to my steady flow data, say we had 50 CFS entering the reach at river station 800. Go ahead and change this to 800, add a flow change location. And then what I want to do here is type in 150 CFS. So this is representing the total flow in the reach from river station 800 and on downward. Now, if we wanted to say, for instance, at river station 500, there was a diversion and half of the flow went somewhere else and half of that flow continued downstream. Then, as you can imagine, we just changed this drop down to 500, add a flow channel, and look, it added a new row for us. We can now type in, we'll say 75 CFS is the remaining flow in the channel that continues downstream. All right, so this is optional. I mean, you do need to have one row here to specify the flow at the very top of the reach, but adding any of the other downstream cross-section flow data like 150 and 75 like I do for River Station 800 and 500. Not necessary. In fact, that's what I'm going to be doing next. So I'm going to go ahead and delete these two rows and start over. So to do that, you can just select the row, go up to Options, and then click on Delete Row from Table, and then poof, it's gone. I'm just trying to, yeah, there we go. Trying to work on the sound effects. Let's go ahead and delete this one right here, which is Reach 800, Options, and Delete Row, and boom, we're back to where we started. All right, very cool. Next up, I'm going to delete the flow of 100 CFS. I'm going to change it to 400 CFS. And then I'm going to add a second profile. So to do that, I just change this number up here from a 1 to a 2. It looks like there's a maximum of 32,000, which seems absurd. I'm not sure who's using 32,000 separate steady flow profiles. Not me. But when you tab off of this field, boom, it gives me a second column right here for profile 2. I'll say profile 2 is 600 CFS. So say, for instance, profile 1 represents the 10-year storm. Profile 2 opens up it represents the 100-year storm. Then we can just keep PF1 and PF2 as it is, or we can change these labels to mean something a little bit more helpful when we're looking at the results. Does the current change between the sections in does the current change between the sections in study? Yeah. Yeah, if you're talking about like the flow rate. So for instance, look at that previous example where I had, say, 100 CFS coming in, and then it increased to 150 CFS, and then it decreased down to 75 CFS. Then, yeah, because there's more flow, you're going to have higher flow rates, of course. That's what we're specifying. But we're going to have a higher water surface elevation, higher energy, higher energy grade line, probably a higher depth of water. The velocity would probably be higher, at least in certain spots. The velocity profile within the reach, that's kind of tricky. I'd have to actually map it out. But I would say that the maximum velocity at any single point would probably be higher with the higher flow rate. Does the current change? Yeah. So when you meant current, I believe you meant like flow rate. So hopefully that answers your question. If not, just keep on typing and I'll just keep talking. All right. Say for instance, I wanted to change the PF1 and PF2 labels to mean something like 10-year and 100-year. Not a problem. I can just come up to Options and then click on Edit Profile Name. And then this dialog box popped up. These are just text I can change. So let's go ahead and delete that. And I'll say 10-year. And then down here, I'll say 100-year. Okay. And then click OK. These labels have now updated. So we have 400 CFS and 600 CFS for our 10-year storm and our 100-year storm event. All right. Let's see here. Boundary conditions. So with our reach, we need to specify boundary conditions. And I'm also sort of thinking ahead. So when we actually run the model, we need to specify the flow regime, whether it's subcritical, supercritical, or mixed. Now, you'd only use mixed if, for instance, you're going to have both subcritical and supercritical. But by default, it's set to subcritical. The flow for this exercise is going to be subcritical. We can check that later, but just trust me on this. We're going to go with subcritical. And the reason I bring that up with regard to boundary conditions is because um, if your flow is subcritical, you only need to specify the downstream most cross section, the downstream boundary condition. And if you're dealing with supercritical flow, you need to specify the upstream boundary condition. And if you're dealing with a mixed flow regime, you need to specify both. So just keep that in mind. The reason I'm going to only specify the downstream boundary condition right here is because when I run the model, I'm assuming subcritical flow. All right, our options for defining a boundary condition are shown here. Just these buttons: known water surface, if we want to specify what that water surface is, critical depth, normal depth, and rating curve. Now, in another lecture, I could probably describe all the differences, and I believe one of my exercises or lessons even goes through this. I'll find out which one it is and and add it to the description of the video. But just check out HEC RAS Exercises boundary conditions. You'll probably hear me talking about this. To keep things simple for this model and to just kind of keep things moving along, I'm going to click on normal depth. And now what it's asking me to do is specify the slope at that downstream reach, or the downstream most cross section in this reach, which is going to be at this river station 0. And the entire reach is 0.2%. So I'm going to go ahead and type that in decimal format, which is 0.002, and click OK. So that's all we need to do for boundary conditions. We can add lots of other boundary conditions and options, and we can even specify separate boundary conditions for each profile. And keep in mind, we have the two profiles, 10-year and 100-year, but we're going to keep it simple and just click this radio button to set the same boundary condition for all profiles. Okay, so I'm going to click OK. And everything looks good here for the flow data. I'm going to go File, Save Flow Data. We've already saved it as base. Now it's time to actually set up a plan, run the simulation, and view the results. So I'm going to go back up to the top here. If I go to Run, and then Steady Flow Analysis, this is the dialog box I had up just earlier. And if you want to use a button to invoke that dialog box, it's this one right here. It's a little stick figure that's running on flat surface for steady flow. And boom, here we go. All right, when we go ahead and save a plan, what we need to do is specify the geometry file and the steady flow file, and then save it and click compute. So there's not a whole lot of options. Actually, there is one option here I want to specify, and that is showing the critical depth. So I'm just going to check that and OK. And let me just make sure I'm not missing anything here. Yep, pretty straightforward. All right, let me go ahead and save this plan. So File, Save Plan. And then I'm just going to call this base as well. Of course, if you have multiple plans or multiple different flow files or geometries that you want to save, the title that you give it may be a little bit more meaningful if you know want to say something besides base. But I'm just going to say base, and then also I'll just give the short ID base as well. Okay, well, that's it. I need to go ahead and save and then click on the compute button.
A few moments later.
And that finished up in 2 seconds, so not bad at all. And now it's time to look at some results. So let's go up to View menu. This is really a View Results menu. And all of the menu items, as I understand it, from cross-section at the top all the way down to Profile Summary Table, or even Summary Error Warning and Notes, refers to 1D results, results that of flowing through 1D structures, even if it's a 2D model. So really all of these results can be viewed for our model, even though it's a very simple model. So what I'm going to look at for results in this lecture is cross sections, water surface profile, XYZ perspective plots, as well as profile summary table. So there's a lot of other options, but I just don't want to spend another hour looking at results for such a simple model. See, can you guys see that? Okay, here we go. So I was at this view menu right here. Let's go ahead and click on cross sections. And then let me bring that down here. This is the cross section for the top of the reach at River Station 1000. And if I just change the cross section, let's see, am I in the way? No. Okay. If I change the cross section, you can see it's basically the same depth of water for the entire reach. It's the same cross section. It's a constant geometry, and it's also a constant flow rate. So there's really no surprise that there's no changes in the geometry right here. If we're curious about the geometry itself, we can zoom in, and then if you hold down the shift button, you can pan around. You get the pan hand here. Also, if you want to click on options and then pan right here, these first like 6 options give you the um, sort of zoom or view related options. So you can click on pan, and then you permanently have the pan hand. This is true for a lot of different dialog boxes and controls within HEC RAS. If you don't want the pan hand anymore, you have to go type, or sorry, options, and then click pan again, and you're back to your normal mouse cursor arrow. I like to zoom in just using the mouse wheel. Wheel up is zoom in, wheel down is zoom out, and then hold down control. Excuse me. Hold down the control to pan around. And something else that I've always kind of liked and never really used enough is the measure tool. So if you hold down I'm sorry, shift. I was holding shift to pan. Sorry if that confused anyone. And if I hold down control, it gives me the measure tool here. So I'm holding down control. If I wanted to measure, say, the depth, then I would just like say start at the top, do a single left click. I'm continuing to hold down control right now, and then come down here to the invert of the channel and then let go of control. And then boom, here is the dialog box that popped up. It's telling me that the depth is 2.72 feet. And that's as I dragged it. It may be a little bit off. In fact, I believe it's 2.71, but we'll take a look at that a little bit later in the results. All right. So anyway, it's such a simple model that the results really aren't too exciting, but I wanted to show you this cross-section results page first. Also, you can toggle this cross-section results page at the top by going to this button right here. So it's the exact same as going up to view and cross-section. Okay, the next result is water surface profiles. So here is the water surface profile. Let's see, looks good. And it's just a constant slope. Here's the invert. So this is a constant 0.2%. Of course, the actual slope that we're seeing in this diagram is greatly exaggerated because the actual slope, if you look at the numbers, is 0.2%. But anyway, we have a constant slope, a constant water surface elevation, and we also have a constant energy grade line, or at least we should. In fact, I could probably toggle that on when looking at the cross-section data. So here's the cross section again. I should probably mention that this water surface elevation is just the 10-year event. This is our 400 CFS. But if you're curious about the 100-year event, which is the 600 CFS, you can go up to options and then click on profiles. Now, currently, we're only displaying the first profile for the 10-year event, but we can double click right here. Now we have the 100-year event. So these two should both be showing up in the display when I click OK. All right. And boom, there they are. Trying to zoom in a little bit here and then hold down shift to pan. We have the first water surface elevation, which is 10-year, and then looks like another foot or two above that. We can look at the numbers is right here. This is the 100-year water surface elevation. The symbology can be edited. This is just the default symbology, which really not a huge fan of. I like this, different colors and thicknesses. So to change that, you can go to lines and symbols. I just did a right click here. You see this? Yeah. And then lines and symbols. Okay. And then in this dialog box, if you select, say, water surface 1 or water surface 2, and then change the actual properties. So let's go ahead and make water surface 1 thicker, say 2.5. And I'll go ahead and, yeah, that's fine. So for water surface 2, let's change the color and make it, I don't know, how about purple? And then I'll make it 2.5. And then for symbol, I'll say none. Okay, so I'll click OK. And then boom, here is the updated symbology. We have the solid blue line here for the 10-year, and then our second profile of 100-year is purple, and it's also reflected up here in the legend. Something else I wanted to point out is you can add different variables, some of which we're not even seeing here. So I don't know if you remember, but I told it to calculate the critical elevation when I was specifying some of the simulation options and calculations. We can do that as well by clicking on the options menu, come down here to variables. And if I wanted to see the energy grade line and the critical depth, I can click OK. And then we're seeing the energy grade lines, both of them, and the critical depth in this diagram. I'm going to turn off the one of the profiles just because it's getting a little too busy here. So let's toggle off the 100 year. Boom. And now here we go. So if I zoom in a little bit, we can see the water surface elevation is blue. That's what it was before. This dashed green line is the elevation, is the energy grade line. So that's just the water surface elevation plus the velocity head. And then this red dotted line down here. Can you see that? Yeah. This is the critical water surface elevation, or I'm sorry, critical depth. And this is why we know it's a subcritical flow because one of many reasons is that the water surface elevation is not constrained by this critical depth when we specified subcritical just prior to running the simulation. All right, so that is uh, that is all I have to say about the cross section. Already talked about the, oops, sorry, the water surface profile. Of course, now we're seeing it with the energy gray line in green and the critical depth right here in red. And then, yeah, and then let's see. I also wanted to show the XYZ perspective plots. So this is sort of a isometric 3D view. Okay. And what we can do is kind of control the view by using these controls up here. There's a rotation angle and an azimuth angle. So let's see here. If we let me change the rotation like this, and then okay, not the best at this. So let's see. If I set the azimuth angle to 90, we're looking straight down on the model, just like we were in the plan view here. But if I change this azimuth angle to something lower, then we're actually looking straight on as if we're right there in person on the ground level. Okay. This particular XYZ perspective plot, I think, looks really good when we have bridges, inline structures, lateral structures, and a simulation to run. This is being a steady flow simulation. We can't even animate it because it's just constant flow and a little bit less meaningful when looking at this particular perspective plot. So it's a cool plot. It just doesn't do a whole lot for us in this particular lecture. All right. And the last result I want to look at for this particular lecture, this problem that we're dealing with, is profile summary table. So the profile summary table here shows us all sorts of data. The default table that loads up, there we go. The default table that loads up is this standard table 1, but there's standard table 2, there's culvert tables. These are like predefined tables where it's going to show you a list of different variables across the top, which you may or may not be interested in. And this standard table 1 is the one we're going to be looking at here because it does have information for our different cross sections. We're dealing with river A reach 1, of course. And here is our cross sections from 1,000 down to 100. I'm sorry, 0. And then the profile is 10-year, but we can change that. We can look at the 100-year data beside the 10-year data, just as we toggled it on with the plots. And to do that, you just go up to options and profiles, and then you can toggle on the 100-year data, click OK. And then now for cross section 1,000, we now have the 10-year data and 100-year data. For cross section at 900, we have the 10-year flow data and the 100-year flow data. So you can see the flow rate is this first column here of data. It's 400 and 600 for 10-year and 600 and 100-year respectively. I'm going to go ahead and toggle that off just because it just kind of busies up the table, to be honest. So 1 second. Okay. And now we're back to where we started. There's columns here for flow rate, invert, water surface elevation, critical water surface elevation, and so on. I'm not going to go through them all. This last one here on the end, yeah, you can see it, is the Froude number, so 0.41, or sorry, 0.44, that represents the subcritical flow. And yeah, there's a lot of versatility that comes with these particular tables. You can even customize the table. So when we were looking at the cross section, for instance, and I measured the depth and said it was 2.72, it's actually 2.71. So we could just take the water surface elevation here of 36.71 and subtract 34. That's our 2.71. And of course, that should be the same difference for every single cross section. So 34.71 minus 32 is the same 2.71. All right, well, that is it for this lecture. What we did was create a very simple 1D steady flow simulation. And we created the geometry, created the flow file with the boundary conditions, and then ran the simulation and viewed the results. So that is it for this particular lesson. If you're interested in learning more about HEC RAS, check out some of the other videos I've created on this channel. There's videos, exercise videos, there's tutorial videos. Tutorials basically uh, take one specific topic and kind of focus in on the details of that topic, referencing the user's manual, whereas the exercise videos really focus on a particular project and then use a lot of the different elements and topics described in the lectures, or I should say the tutorial videos, to accomplish something and build a model uh, for that exercise. What I'm doing here in this particular format is a YouTube live stream. It's a lecture just talking about some of the same concepts, just trying something new here and trying to get a view on some of the controls, obviously, as well as reach out to you guys in a live feed. So if you have any questions, you can ask them to me in the chat, even if it's not about this particular topic. There's so few people in the chat right now that I'll talk to anyone. But I want to sort of to build a platform and ultimately put together a boot camp for anyone who's interested in learning HEC RAS from A to Z, starting with what you're seeing here. Lecture one is being something like a very introduction lecture. And then after that, we'd build on this and go to unsteady flow, 2D flow, maybe even touch on sediment and so on. Just a boot camp that will get you running and up to speed with HEC RAS. All right, well, that was it. Thanks for joining me and have a great day.